But now, back to the actual program. So our first speaker today is Emery Berger, who's sitting right here. Emery got his degree in 2002 from the University of Texas at Austin and has done a lot of work in different areas, programming languages, runtime systems. Very influential work. He has won already 2 most influential paper awards, just recently at PLDI 16 for his work on Die Hard. And today he will talk about a slightly different topic, namely the correctness of spreadsheets, which is a very important problem in practice, and he has done super interesting work in this area. So welcome, Emery.
Should be good. It's HDMI. On. Great. All right, welcome everybody. So today I'll be talking about spreadsheets, as Peter mentioned. A little joke there about it being an excellent problem for PL researchers. So this is work that's mostly joint with my graduate student, Dan Barrowy. Dan is actually graduating this year, and with my longtime colleague, Ben Zorn at Microsoft Research. So before I get into this, I'm curious to know, how many of you know who these people are, Reinhardt and Rogoff? Okay, great. So it turns out that these 2 people were unfortunately highly influential. So Ken Rogoff is the guy on the left, and it's Carmen Reinhardt on the right. They're both now professors at Harvard, which is sort of down the street from us, if you will. And they wrote this white paper, which they called Growth in a Time of Debt. Growth in a Time of Debt had this, this sort of conclusion, because economists don't understand the difference between causality and correlation. I'm not being taped, right? Okay, so anyway, so what they argued is that once a country's GDP ratio exceeded 90% of debt, that is, the debt load became too high, then countries entered this death spiral where they would be in low economic growth and could never get out. So this white paper, which actually formed the basis of a book, proved to be highly influential. This is Paul Ryan, who's the Speaker of the House in the United States. He used this to support an austerity budget, which thankfully did not go through in the United States, but did go through in other countries, namely Greece, where it was met with great celebration. So you might wonder, what kind of analytical software did they use to do this sophisticated analysis? more particularly, what programming language did they use? And the answer is not C++, despite what you might think. So C++, obviously a popular language. It's in use by about 3.5 million people today. They also did not use Java. Java. So Java is also a popular language. It's actually more popular now than C++. It's in use by about 9 million users. And of course, all of you know where this is going. The language that they used is Excel. So Excel, it's really easy to write hello world in Excel. You just write it. It's quite a popular language. It's got 500 million users estimated. That's just Excel. Obviously, there's also a Google variant, which is Google Sheets. And just to put this in perspective, this is 7% of the world population that are estimated to use Excel. So spreadsheets really are everywhere. They're in all domains. They're widely used, as I said, not just by 500 million users, but they're used not just to keep track of movies I watched on Netflix, but also to determine things like economic analyses and government roles. They're widely used in academia, of course, as well as in science. And the part of the reason for their success, or the success of Excel and why it's got so much penetration, is that it's a really simple-to-use model. At heart, Excel is a functional reactive programming language that dates back originally to VisiCalc, so preceding even the term reactive programming. And it's intertwined with data. And you can just sort of have your data right there, and you operate on it with formulas, and it's very, very convenient. And so the barrier to entry is very, very low. So spreadsheets, they're really, really important, but the very fact that it's so easy to just type things in and get your formulas in place and have the data all on the sheet means it's really, really easy to make mistakes. And if you couple the ease of making mistakes with the fact that they're everywhere and being used to make important decisions, this is obviously a recipe for disaster. All right? So I contacted Reinhardt and Rogoff to get their spreadsheet, which was not publicly available. So I can't distribute it, but you can see a screenshot. So they did this, they, by which I mean grad students, did this analysis where they included data. I don't know if you can see this. It says 1790. So they went and they did all of this data analysis that they gathered data from all sorts of sources going back to 1790 for a bunch of different countries. So there's actually like 25 sheets in here full of data, full of formulas. Paul Krugman, the Nobel Prize-winning economist, who's a columnist for the New York Times, after this analysis came out of the spreadsheet, they discovered that there was a deep problem, in fact, many deep problems with the Reinhardt-Rogoff spreadsheet, suggested that this may have led to what he called the Excel depression. And he asks, so did an Excel coding error destroy the economies of the Western world? So the answer is yes, or at least partly. So what happened is that a group of my colleagues actually at UMass, in fact, in the economics department, obtained the spreadsheet and did a manual analysis of the spreadsheet for months, trying to ascertain what on earth was going on that led them to the conclusions that they came to, because the UMass economics department is famously left-wing, and they still have a class on Marxist economics. And they simply didn't believe the claims that austerity was going to be this magic solution that would solve all of the world's problems. And so given their skepticism, they sought the data. They actually tried to reproduce the analysis beforehand and couldn't reproduce the analysis, which led them to reach out to Reinhardt and Rogoff and get the spreadsheet. And what they found when they redid the analysis, that is, they recorrected it, if you look at the blue bars are these estimates for these brackets. They basically binned these debt GDP ratios into different categories: less than 30%, 30 to 60, 60 to 90, and death spiral 90% plus. The blue is the original analysis, and the red is the corrected analysis. And as you can see, this is the death spiral predicted by Reinhardt-Rogoff, where things go negative, and things are actually still okay in the corrected analysis. So the conclusion is actually unwarranted that austerity would be the solution to this problem, since there was not actually a problem. All right? So the question is, could we possibly have prevented this? Right? This is an analysis that was done on this gigantic, gigantic spreadsheet, and the people who did it thought they were doing a good job. But there was really no way, short of hiring people who were their adversaries, to manually conduct an analysis for months to actually detect these problems. That clearly doesn't scale, right? So, what I would like to propose is that we actually try to solve this problem. Given the fact that spreadsheets are so widely in use and they're not going anywhere, and that they're being used for such influential influential domains. They're being used for science. They're being used to guide policy. We really should try to address how we can make the world a better place. And so my proposal is that we use programming language technology, treating this as a programming language, because it is, and try to find problems in these spreadsheets before they leak out and destroy the world. All right? So what's the problem? So let's dive in a little bit into the spreadsheet. So here's this big spreadsheet. The basic problem here is that, surprise, people make mistakes. The program can be wrong. That is, the formulas themselves may be wrong. The data may be wrong. And in the case of the Reinhardt-Rogoff spreadsheet, both were wrong. So there were incorrect formulas and incorrect data. So one obvious problem is just straight-up input errors. So I'm typing stuff into a spreadsheet. Human beings aren't perfect. And it turns out that the error rate is actually pretty predictable. So on average, these numbers, the precision seems unwarranted, but it's actually accurate. It's 1.2-ish% of characters get mistyped, which means that if cells are roughly 5 characters, you get cells mistyped at a pretty high rate. So this guy, Panko, is a professor at the University of Hawaii who's done a lot of research on uses of spreadsheets, not programming language analysis per se, just uses of spreadsheets. And he'd conducted some small-scale user studies, as well as groveling over some spreadsheets, and concluded that the percent of cells mistyped is about 5% on average. In other words, if you have 20 cells, one is probably wrong. We actually did a large-scale experiment that I'll describe in a minute, and got almost the exact same numbers. So this is a pretty robust finding. What this suggests is that for any reasonably large spreadsheet, and 20 is not that big, at least one typo is virtually guaranteed. Right? So that typo obviously could be something that's in the data. It could be a data element entry error that doesn't matter, like it could be 1.0001, or it could be something that really matters, like 1001. Right, where you leave off the decimal place. So these things can have huge impacts. Of course, input errors are not the only source of errors. When you are using Excel, it's very easy to make copy and paste errors. It makes it easy for you to replicate formulas by dragging. There's a lot of complexity, actually, that is built into the user interface that leads to all sorts of errors. They're convenience functions, but they can cause problems. All right, so spreadsheets that matter have data and formulas. There's spreadsheets that just have data. You'll find these. These are basically like poor man's databases. That's fine, but usually those things aren't used for anything really important. The things that matter tend to be composed of both data and formulas. So the Reinhardt-Rogoff spreadsheet is pretty big. It's got 100,000 cells, and there's about 20 sheets. It sure would be nice if when you were using, this is an office product, right? So you could imagine Clippy comes up when you're typing, and it says, hey, there's something about to go wrong, and it warns you when you're about to make a mistake, right? It's unfortunately not at all obvious how you do this, right? So obviously, if the English is misspelled, it can just look in a dictionary and say, oh, that's wrong, or maybe do a grammar check or something. But for formulas and data, not so much. So why not? So first, this is a programming language. Like most programming languages, there typically are no specs associated with them, right? Not even comments. So there's no specs, so we don't know what the program's supposed to do. We don't know where the data came from, right? The data could come from any place. So you can't make any assumptions like, oh, this data is normally distributed, or it's uniformly distributed, or what the min or what the max is, and all of these sorts of things. So in the database world, this is better controlled. So you have these schema, and the schema might say, for example, that the min or the max is this value. In spreadsheets, you don't have that. That's not entirely true. It's available as something you can actually do in Excel, but 99% of spreadsheets don't have any use of such functions. And finally, given that you don't know anything about the data at all, you can't take advantage of this notion of outlier analysis. So again, in the database world, there are some techniques that you can use to clean the data, and none of those techniques apply here, unfortunately. All right, so I'm going to talk about two systems today, one in some depth, and then one which is actually ongoing work in less depth. The first I'm going to talk about is a tool that we call CheckCell. So CheckCell is aimed at finding data problems. So what it does is it analyzes the interaction of data and formulas. Now you may ask yourself, how on earth can I find a data problem? If I don't know anything about the distribution, I don't know mins, I don't know max, I don't know anything. So the trick here is that what we're going to do is, rather than just trying to look at the data in isolation, we're going to look at the data and how it plays with the formulas. And in particular, we're going to use the fact that there's formulas operating on the data to automatically identify cells that have an unusually high impact on the results of those formulas. So I have some formula, like sum operates over a bunch of data. I would like to know which data elements in sum lead to big changes which data elements in that range lead to big changes in sum. And of course, sum may be used by something else, something else, something else, and we're going to analyze all of these interactions. So the insight is that if you identify these cells with unusually high impact, there are two choices. One is that it's really important. That data value really matters, all right? So that's good if that was intended. If it wasn't intended, then it's probably wrong. Now, you can also turn this around and think, well, what about the cells that don't have high impact? Those cells don't matter, right? So this is focusing the attention of the user on exactly the data elements that have the most impact on their computation, right? So let's go back. This is actually a spreadsheet we spidered off of the web, which is incompletely anonymized, as you can see here. These look like social security numbers, which is illegal. But the point here is that this is a class. I'm only showing 48, or actually fewer than 48 students, but it's pretty typical to have classes with hundreds and hundreds of students. It's very easy to screw something up. I speak from experience, all right? Bitter experience. I actually have to confess that I made a mistake in a spreadsheet. It was called to my attention by a student, and when I ran CheckCell on the spreadsheet, which I had not bothered to do beforehand, it immediately found the problem. I was like, oh well. Luckily there were no other problems, by a miracle. Okay, so the point here is that manual auditing just doesn't scale in general. So if you have a spreadsheet that has just 10 entries, you can go over every data element and figure out, oh, this is correct or this is not. If you have thousands of data entries, this clearly doesn't work. So I'm going to make a simplified version of this spreadsheet just for the purposes of exposition. This is as if I had exactly one student instead of hundreds. This would be awesome. So here I have a bunch of grades. You can see homeworks and quizzes and exams, and there's a final grade, and this pass-fail is a little bit of a joke. But if the way it works in grad school in the United States is that your grades have to be pretty high for a grad class to count. So at UMass, you have to have, I believe, a B+. So if you get below a B+, it's the moral equivalent of failing a grad class. So here, this would be like a B, which means the person failed, which is sad. In the upper left, I actually have the CheckCell window open. And so this is a plugin that actually you can load as an add-in into Excel. You click on this Analyze button, and then it goes and it performs this analysis, looking for errors. And the first cell it comes up with is this bottom one, 78. It highlights it in red, and then you can say, I'd like to fix the error. If you know what the data is supposed to be, you can go ahead and enter what the corrected value is, and then you can move on. It marks it in green, and then it goes to the next found error, or the most important thing according to its analysis. If you say that one is fine, you can mark it as OK, and then finally it concludes. Right, so that's the workflow. Right, so how does this work? So the first thing it does, so we have to grovel over Excel, which is not the nicely behaved programming language you might think it is. It turns out that Excel is surprisingly complex. It has 3 different ways of addressing cells, and it has these things called absolute references as well as relative references. It has array lookup. It has R1C1 format, which is, instead of using cells in like A5 coordinate space, it actually uses this relative row and column numbering. So it's fairly complicated, and we built a tool to handle all of this mess. But the first thing we do is we build up a dependence graph, and we grovel over the whole spreadsheet, and we build up this graph. All right, pretty basic once you have gotten all the stuff out of Excel. And then what we do, so if you look at the spreadsheet, let me just show you this particular grade, which is the one that gets highlighted by CheckCell as the most important. If you look at the data, you can actually see 78 is not even obviously an outlier, right? It's in the range of the homeworks. It's not a crazy number. It's not like the homework grade is 1 million or -12 or anything obviously wrong. So it's not obviously wrong. And of course, you can't assume that these grades from an individual follow any sort of distribution, like a normal distribution, which might work in aggregate, but certainly doesn't work for an individual. So what Checkcell does is it actually goes and it grabs every range in the spreadsheet that feeds into any of these dependencies. All right, so if I have a range, like a sum or an average, then that's going to be computed on a bunch of stuff. This is what it's going to do. It's going to look at this range and focus its analysis on range one at a time. Okay? We use a technique that we call a Bootstrap-based impact analysis. So this adapts a statistical technique known as the Bootstrap. How many people here have heard of the Bootstrap? Okay. Some, that's good. So the Bootstrap is a really, really cool statistical technique. It was invented by Bradley Efron in 1979. It's been extended in a lot of ways. The technique is somewhat counterintuitive, but super cool. The idea basically is I would like to understand what the value is of a statistic over a population, like normal, but I don't know where the population is drawn from. I know nothing about the distribution. Right? And in fact, all the data I have is the data I currently have. I can't go get more. So the way the Bootstrap works is it basically gins up new samples from the original data sample that you have and allows you to compute a statistic over this sample, the many samples that you've created as if by magic from the original sample. All right? And the way it does this is through a technique called resampling, and I'll show it graphically in a second. One of the great things about the, well, there's many big great things about Bootstrap. So it's non-parametric, which means that it doesn't depend on any sort of a priori known parameters, such as the mean, standard deviation, any of the parameters of a standard distribution like normal. And whatever samples you get are definitely going to be from your population. This is crucial because we don't know the ranges of any of the data we're looking at in a spreadsheet. We know nothing about it. All right. So let me show you how the Bootstrap works. So suppose f is some function that operates over this range and decides whether somebody is failing or passing. This is actually a combination of weighted averages, right? So here, right now, currently, it says that we fail, but if we changed a value, it might be that we would get a different result. That seems normal. So the way that it works with the Bootstrap is what you do is you randomly choose an element from this distribution, from the range, and you do this over and over and over again until you've got the same number of elements. Right? So this is resampling with replacement. That is, I go and I get one, I don't take it away, I just go and I get another one, another one, another one, and I do this over and over and over again. So here is a new sample. In this sample, I pass. In this sample, I pass again. And in this sample, I fail. All right? When you do this a bunch of times, computers luckily are fast, so we can do it many, many times very quickly. In fact, in Checkcell, we do it 2,000 times for every range, roughly. You get a bunch of results. And so this distribution is the distribution of the original population. And it turns out that there is, with the Bootstrap, we don't know what the n should be, but if n is sufficiently large, then it converges on the actual statistic for the population as a whole. All right? So we now can actually claim with high likelihood that pass is more frequent than fail, but fail is relatively frequent. So this is what Bootstrap gives us. So what Checkcell does is it actually goes and it takes all of these distributions and it partitions them cell by cell. So these resamples, a bunch of these resamples will not contain the very first entry, right? Because I'm randomly choosing. Some number of them will not contain the very first one. Some number will not contain the second, not the third, et cetera, et cetera. So then we can have, in this particular case, all the ones that exclude 78. So here, if 78 is not there, it turns out that pass rate goes way, way up. We get a sharply different distribution. So this suggests, and you can do a statistical analysis to compute the likelihood of this, that in fact 78 has a significant impact on the result. It's highly impactful. All right? And the way that we look for this is we actually go and we look at the resulting distributions. We say, what is the likelihood what's the p-value associated with getting this thing. If it was the original distribution, if it's less than 0.05, then we say, this looks like a significant result. It's unusual. All right? So the heart of the technique is we build a dependence analysis, we go through the ranges, we do this resampling, and then we discover which entries have an unusually high impact, statistically significant impact on the final result. All right? It turns out that we can handle things that aren't just numbers. In the paper, we talk about how we deal with string outputs, and of course, there's a bunch of things that come up as statistically significant, and you need to rank them by their impact. And so we talk about how we do that in the paper. So Checkcell works pretty well. We've run it on a bunch of different spreadsheets. There is, however, this problem, which is that unlike in the world of ordinary program testing and debugging, we don't actually have ground truth. Typically, it's like, here's a bug, this is what it's supposed to do, and then you say, oh, I'll see if I can find the bug. We just have a bunch of spreadsheets, and we have nobody to whom we can ask, hey, is this spreadsheet correct or not? So that's unfortunate. So what we ended up doing was we ended up injecting errors in these spreadsheets and then observing whether Checkcell could find them. Now, I should add, we did this on some real spreadsheets as well, and of course, we ran the analysis on Reinhardt-Rogoff, and I'll mention that at the end, but I just want to talk through this because it's kind of fun. So the question you should ask whenever you hear anybody talking about error injection is, are these errors representative? Like, you injected errors. What did you do? Do people really make errors like that? And the answer here is yes. And the reason we know this is that we got people to make the errors. Okay, so how many of you have heard of Mechanical Turk? Great. All right. So briefly, for the few who didn't raise your hand, Mechanical Turk is this service from Amazon that lets you hire people online to do tasks. And they call these tasks HITs, or human intelligence tasks. So you can work as a Mechanical Turk yourself. I recommend against it. The pay is not that great. But crucially, you can get results. There's all kinds of crazy stuff on Mechanical Turk. So here is one that I grabbed where people are supposed to say, what is the name of the product being advertised? And you see this picture of these hipsters starving, apparently. So it's not clear. But anyway, a computer certainly doesn't know. Maybe a person would know. And then you can enter all this information. You get a certain amount of time to do it, and then you get paid a whopping 6 American cents per hit, which is it's pretty typical. All right, so here's what we did. What we did is we actually went and took a ton of spreadsheets. So there's a big repository of spidered spreadsheets, and we extracted data from them. And then we turned the data into images and had people retype it. All right, so it's a little hard to see, but there's 10 cells of entry here, and people had to actually type in these values that are in like in CSV format and write them into the cells. So it's as if they were just transcribing them. And because they're presented as images, they can't just copy and paste them. So they really are looking at an image and writing it down. And arguably, this is even better than it normally is, because usually you have something or some other window or something, and you're copying. Here, it's right in front of you. So you'd think, oh, well, this is a good situation. So we ended up gathering about 170,000 retyped strings. And then from that, we built a very simple model that allows us to generate typos. So given some string, we can say, what is the likelihood that it would be this other string? And so we can actually trigger these errors at a desired error rate. And the error rate we used was the error rate we observed from people. All right, so we have human-created errors. Things like they meant to type a 5, but they typed a 6 because they're right next to each other. And then we could inject them into cells. Right? So for fun, we decided to compare against a Gaussian strawman. And the Gaussian strawman, we only compared against numeric inputs. The idea here is that Gaussian lets us do things with typical outlier analysis. If something is more than so many standard deviations away from the mean, we can declare it to be an outlier. All right? So here, X, if it's in the tails, we say it's an outlier. So we compared Checkcell against this Gaussian. The Gaussian locates outliers in input data, whereas Checkcell, remember, locates data that has an unusual impact on the formulas. Right? So they're operating in two totally different spaces. So briefly, it turns out that Checkcell is correct more often. I don't want to go into too much detail. Checkcell is on top. Higher is better. We get more and more precision as the error increases. Its recall is higher. So as the total output error increases, total output error, meaning the error from the formulas, as that gets worse and worse, Checkcell finds more errors, which is what you'd expect, because Checkcell is specifically looking for big differences in output. And then if you wanted to fix the spreadsheet one at a time to correct these analyses and you wanted to lower error, it turns out that the amount of effort for Checkcell is actually pretty minimal. So it's roughly comparable to the Gaussian. It's also fast. So most of the time it takes a couple seconds. Reinhardt-Rogoff is an enormous spreadsheet. That's the one way at the end. It takes a long, long time. But it doesn't take months. It takes minutes. So we ran it on Reinhardt-Rogoff, of course. And I actually, since we had the luxury of having colleagues who were intimately familiar with the Reinhardt-Rogoff spreadsheet on campus, I had one of them come by before we ever ran the analysis to tell us what he thought of the analysis. So as soon as we ran the analysis, we got this big red thing over here. And he looks at it, he kind of squints, he goes, "Oh yeah, Norway." We're like, okay. And he says, "Oh yeah, Norway. Yeah, we wrote about this." And so I actually didn't know, but they had written up this gigantic takedown, not just the little version, but a really, really long one that went into every single error in excruciating detail, which is actually pretty awesome. And it turns out that it actually exposes a methodological error. So the thing is, in fact, riven with errors, but in particular, it turns out that there is this one data element that accounts for 5% of the weight of all of the years. Remember, it's from 1790 until the current day. So it's a lot of years. But it's actually only 0.2% of the country years in the category. So it is, in fact, a value that has a gigantic impact on the final result. And if you correct for it methodologically, a lot of the result that they declared goes away. All right? So Checkcell found a bunch of other errors. They all turned out to be actual errors in the spreadsheet. I don't feel like this is a terrible spreadsheet. All spreadsheets have these errors because people are fallible. But we were quite satisfied that it was able to find all of these errors, and in particular find the ones that really mattered. So you can actually download Checkcell. It's available at checkcell.org. But Checkcell is really all about finding data errors, and data errors really do matter. But of course, Excel and spreadsheets in general, not just about data, right? They're about data and about formulas. So here's a spreadsheet, and I assert to you, this is a real spreadsheet, by the way, about a tobacco settlement trust fund. And it's got a bug, and many spreadsheets do. But it's not a data error. What you can't see is that almost all of this data here is actually calculated. This is all from formulas. So we would like to be able to not just find data errors. They matter, but that's not everything. Let's find formula errors too. But there's this problem. So unlike in a conventional language, basically Excel programs are correct in some sense no matter what. Right? So unless there's a circular reference or a divide by zero or something like that, all the formulas are valid. Right? They all compile. They all run, if you will. It's just that the results are wrong. Right? So how do you deal with a language that is, in a sense, so clean that everything sort of works, right? There's no seg faults. There's no null pointer exceptions. But you've got bugs. So this also seemed like a hard problem. Again, we have no specifications. In some cases, you might see something and you say, well, is this total really a total? Do I need to understand English to be able to actually understand the intent of a spreadsheet? That's one possible approach. We did not go down that path. But understanding intent seems like that would be required, and that's horrible. Right? There's no way to ascertain the intent for sure in these spreadsheets. They're rarely as clean as this, and we can't ask people. Right? So what we ended up doing was adopting a quite different approach. So we call this technique excellent. I apologize in advance. So our intuition was that the formulas that are likely to be wrong are unlike formulas that are, like, if there's a bunch of formulas in the same neighborhood, if you will, and one is slightly different, then that one is probably wrong, right? That's the intuition. Now, we don't actually embed this as a rule. This is, again, much like Checkcell, something that we deal with statistically. But here is what excellent does. Let me read it to you. it identifies this one, which it marks in red. The green ones are proposed fixes. And it says, excellent thinks that this formula, which says sum D6 to D16, should look more like address B17 or E17, and it says what the formulas are. All right? So how does it do this? The way that it does it is it actually goes over the whole spreadsheet and somehow, as I'll describe in a second, identifies these locally anomalous formula shapes and then connects them up to the things that they are closest to. All right? So here, if you look at the formula, you'll see what the problem is. This is the correct formula. That is the formula that Excellent thinks is the proposed fix. And oh, by the way, many people don't realize this, but if you hit Control backtick in Excel, then it exposes what's called the formula view. So you don't just have to see the data and go over cell by cell to see the formulas. You can actually see all of the formulas. So this makes it a little easier. That said, we've looked at all of these spreadsheets that we've analyzed, just eyeballing them in formula view. It's helpful when you know where the problem is. It's not helpful to find the problem. All right, so here is the correct one, and here is the marked bug. And so you can see that the marked bug includes the title and includes some space above, and it includes some cells which are currently empty. But if somebody put a value in one of those cells, obviously it would be wrong. This is clearly not a likely catastrophic error, but this is just meant to give you a flavor of the kind of things that Excellent can detect. So crucially, like I said, there's no hard-coded rules. We're not doing something like saying if the ranges are somewhat different in this regard or some other ad hoc rules. Everything is statistical, and it's done over their structures and their location. So briefly, what we do is we do a kind of spectral analysis. We actually encode the whole spreadsheet as if it was made up of vectors. So spreadsheets, in a sense, already are made up of vectors structurally. That is to say, you have a formula, and it depends on something. So we literally draw a vector from the formula to its dependence. And then we compose all of the formulas. We get a resultant vector, and we encode the location of the cell. And all of this turns into a matrix that captures simultaneously the structure of the formula as well as locality. And then we can actually perform this spectral analysis. This is something this is mostly a debugging tool, but this actually is available to the user if they want. And you can see these are histograms, and these mean that these are cells, again laid out in some sort of, just sort of flattened as if they were in one axis instead of 2 dimensions. There's a lot of formulas of this shape, a lot of formulas of this shape, et cetera, and you can see kind of down here, there's this tiny little thing. That is an outlier. All right? And so that one right there is quite close to this one. And it identifies the thing that it's closest to structurally and in terms of its actual geometry on the spreadsheet as being the likely correct thing. All right? So we've been working. Actually, I spent a good chunk of the summer at Microsoft. We met with the product group. So we're working right now on trying to get something like this ready for them to actually play with and potentially incorporate into Excel, which would be great. So I want to sum up just by talking a little bit about some infrastructure. So we built a lot of infrastructure to get all this stuff done. This is really reusable infrastructure that anybody in this room could pick up and use if you want to do any sort of analysis on spreadsheets. So a lot of this stuff just didn't exist, so we had to write it ourselves, but now you can take advantage of the fruits of our labor. All right? One of them is something we call Parcel. So Parcel is a complete parser for Excel cell formulas. So if you throw an Excel cell formula at it, no matter how crazy, it'll convert it to an AST. Right? That actually is a tremendous amount of engineering that you would not have to do. Trust me, you don't want to do it. So this is a quite nice little piece. Then Dan, in his own GitHub repo, has Depends, which is a really unfortunate name, but I'm not going to explain why. So it's a dependency analysis tool for Excel, and you can actually take an Excel spreadsheet and it converts it into a dependence graph. So it actually uses Parcel as well. And finally, all of the check-cell code and some of the Excellent code is actually available for download. It's in this directory data debug under the Plasma UMass repo, which is my group's repo. And so that has all of the stuff neatly partitioned out for how you build these plugins. So if you want to build a plugin for Windows, for Microsoft Excel, I mean, then you can just use part of this project. Everything is written in C# or F#, mostly F#. So if you like functional programming, it's actually really, really nice. It's practically OCaml. And now F# runs on everything. And in any event, it's very clean code and easy to adapt. And so with that, I will conclude. This is my group, Plasma. We're hiring grad students, by the way. And UMass also is hiring this year. So if you are a person who's interested in building systems, especially for data science, writ small or large, you should contact me. All right, thanks for your attention. I'll just repeat your question. It's okay, I'll just repeat Martin's question.
So when you're sampling, you have to generate new data, basically, right? But I think in all these works, like Synthesis, like one of the troubles that you see with Excel is that you don't know what the format of the data is. So if they put the date in certain shape, or there's many ways to write the date, for instance, so there's different formats. You have to know the format of the data in order to generate it. How do you?
Right, so the question is, how do you regenerate, how do you do this resampling where you're regenerating data when you don't necessarily know the formats? So the quick answer is that we actually just take the data as it is in the spreadsheet, and we just use that data, right? So if you have 10 things that are entered, we're not really creating new data, we're just grabbing one of them and reusing them. But in fact, it turns out that Excel, while it has all these formats, it does these kind of crazy silent conversions. So there is an internal value, like you see a format, and there's a format which is kind of a style, if you will, and then there's the internal data representation. Sometimes when you convert something, then it changes the value altogether, and you can never get it back. So if you enter something in, if you change it to a date, then it becomes, like if you have a string and it turns into a date, then that becomes a number, which is the number of days since, I think, Jan 1, 1970. And then you're lost forever. But anyway, we bypass all of these issues because we actually go directly to the data.
It's only looking for errors in the data, but it seems one of the errors, at least, that you uncovered wasn't really that, right? I mean, in the famous spreadsheet, which I've forgotten the name of already, sorry, I mean, the data was correct, if I understand correctly, but the methodology underneath was wrong.
Right, so the question is, you said Excel is really about data, but the error that you described in the Reinhardt Rogoff spreadsheet, at least the first one, didn't seem to really be that the data was wrong and exposed a methodological error. So you're absolutely right. So we did find a number of data errors as well, but it just turned out that it is just examining, right, the interaction between the data and the formulas. And so if you have a number and that number has an unusual impact, it could be wrong, it could be really important. It could be, this third possibility, that you just did something weird with your formula. So it is true that the data itself can indicate some problem with the formula. And they did some very goofy things. So the binning, they didn't weigh things in the binning. So if you said there's 30% category, 60%, et cetera, country by country, if Spain, for example, had spent 50 years in the 30% GDP category, the debt ratio category, and Norway had spent 1, those were treated identically. So the average was treated exactly the same. So there was no weighing whatsoever. So that's actually one of the methodological errors that that particular result exposed.
Yeah, have you looked at the chain of error propagation at the length of it? I guess what I'm trying to get here is, if you have small errors, they can add up to something catastrophic potentially. But you said that you only study big, large errors that are clearly going to screw up your results.
Right. Okay. So the question is, if you do you look at the length of the chain of these things, because you could have a small error that propagates and becomes a big error. So the answer is, in fact, the only thing we look at is the final results. So originally, we actually were looking at, well, let's see what happens with these things as they propagate up. But then we realized, well, why are we doing this? The only thing that matters is the final result. And so we only look at the final result. So if you have some error here, and there's a problem with this potentially. And the problem is very simple to explain. If I have something and it is this problem, and that problem doesn't cause a big change here, but that change ripples up, then that's something we'll capture. However, if you have death by 1,000 cuts, right? You have a bunch of things that are slightly wrong, and they all combine and produce something that's a problem, we cannot find that kind of error with the approach that we're using right now. And the reason is simply because we look at the end, and we don't look at the intermediate steps, and this is just a precision recall trade-off. So we could clearly find it, and we could increase the recall, but we'd dramatically raise the false positives.
Do you have rates of the false positives? How much do you increase?
Yeah, so the graphs that I showed actually are based on the injected error, so I have them, they're all in the paper as well, yeah. It's a complicated situation actually, because if the CheckCell is designed, so the question was, do you have the false positive rates and false negative rates? They're in the paper, bugs in our framework are about impact. So the really important thing is to capture things with high impact, so we weigh the impact. So all bugs are not created equal, is basically what I'm saying. Yeah.
When you ran the Bootstrap, you said you did it maximally 2,000 times, right?
Yeah.
But if your data, I don't know, if you want to identify one error or one error in one cell, and your data or your range is like, I don't know, 10,000. I don't know. I would rather do it like the range of the size of the range times 30 or something.
Yeah, no, you're right. In fact, the way we do it, so it turns out that you can easily compute the likelihood that a particular cell will be included. It's 1 minus 1 over n to the n, where n is the range. That converges to, if I recall correctly, it's 1 minus 1 over e. So we actually multiply the range size by e, if I recall correctly. And that guarantees that we're going to get a partition with enough stuff in it. So we do actually do that. Yeah. When I said 2,000, that's what we do for small ranges, and then we have to scale up for bigger ranges.
So you said that if you find these values that have a high impact, either important or wrong. Have you thought about looking for values that's supposed to be important but it is wrong and then don't have the impact? So like the other way around.
Right. So the question is, so right now CheckCell operates by finding values that have high impact, which are either important or wrong. Have you looked at trying to find things that have that are the opposite, that should matter, but don't? We haven't. I don't really know how we would do that. So this question of missing data is a tough one. So in a sense, if there's data that should be there, if it's not present in the spreadsheet, our approach can't find it, and it's not really clear how you would impute it. But we are interested in other things. For example, one thing that we've observed in some of these spreadsheets is that in some cases you have a number instead of a formula. And it's clear that that should have been a formula. And God knows what is going on in somebody's head, but they actually just put in the result instead of the formula. And so being able to say, clearly this is an error waiting to happen, if you will. Right? So you have a number, it's hard-coded, it should be computed, you change something, and this doesn't get recomputed. That's not good. And so some of these things we can actually find if they're the same value. They're often not the same value, and then figuring out what went wrong is an interesting question.
Okay, a question. So the Excel format is known to be proprietary. I don't know what it is, but would actually Microsoft consider it's not already kept to keep somehow versions of how the data came into Excel, because this looks like very interesting.
Oh yeah, absolutely. So the question is, so first the Excel spreadsheet format is proprietary. That's not entirely true. So the modern Excel spreadsheet format is actually in XML. So if you see .xlsx, that means it's in XML. But it doesn't matter. We actually typically just operate directly through Excel. rather than through the spreadsheet itself. But you point out something that would be terrific, which is what if there were versioning information? What if there was some information about how the spreadsheet evolved? And that would be amazing. Definitely if there was something that captured this evolution, it would be very easy, for example, to discover copy and paste errors. Or drag and drop errors or accidental overwriting of formulas and things like this. So some people in the software engineering community have been looking at like GitHub repos. If there's something checked in, then you can compare these things over time and maybe find problems. But it's not currently baked in. But yeah, it would be terrific. It would be very helpful. And I have to imagine, honestly, for legal reasons, it would actually be quite desirable. So there are a number of federal administrations in the United States that are forced by this legislation to require a lot of details about the provenance of data. And having versioning seems like something that Microsoft should add. But I'm not in charge, so someday. What is the most typical? What is the most painful error that we typically don't find? Yeah. So let's see. I mean, in fact, part of the motivation for Excellent was problems that we couldn't find with Checksell. Can we find every error? No. That's clearly never going to happen. But the big pain points really are things like catastrophic financial errors. And it turns out these are very, very easy to create. But that's a good question. I don't really have an answer for you simply because there's a bunch of errors. People find errors all the time. Clearly, you could make some sort of ad hoc thing that finds a particular error. For example, there was just some problem that was exposed by where people were using they were using Excel as a poor man's database for gene information. And because of these automatic conversions I described before, there were some genes that were like 04 MAR, and it said, oh, 4th of March. And it converted them for you, for your convenience. And unfortunately, that got converted into some number, and when you save it as a CSV, it actually turned into that number, which is the number of days since Jan 1, 1970, which is not a particularly useful thing for genetic analysis. So there's sort of more errors all the time with Excel. But our aim is to find ones that are likely errors without any sort of ad hoc, this is the error we're looking for. And hopefully we can uncover a significant and useful class of errors.
Oh, thank you.